In this video, I'm going to show you how to use Newton's method to approximate a solution. To begin, I'm going to show you how to use Newton's method pictorially, and then I'll show you how to do this algebraically. So let's begin with a function. And on this function, I want to find the root, which is here on the x-axis. So we're going to start with a rough initial estimate, x1. So let's say the x1 is over here. And what I do is I'm going to go up to the curve from x1. So it goes up to here. And where it hits the curve, I'm then going to slide down the tangent. And I'm going to slide down until I hit the x-axis. Where this tangent hits the x-axis, that is now x2. And we can see that x2 is a better approximation than x1 since it's closer to my root. I'm going to repeat the process again. So I'm going to, from x2, I'm going to slide up or go up to the curve until I hit my curve. At that point, I'm going to slide down the tangent until I hit the x-axis again. And this will be my x3. And then I'm going to continue this process until I get closer and closer to the root. So I'm going to go up to the curve. Where I hit the curve, I'm going to then slide down the tangent. And this will now be x4. So as you can see, as I go up, slide down the tangent, go up and slide down the tangent, I will get closer and closer to the root. Now, this works well in nice cases. Now, it is possible sometimes for things to go wrong. So in this next picture, I'll show you how this could happen. So let's say that we start here at x1. Actually, I'm going to change this. And I slide up the curve. And then from here, I'm going to slide down my tangent. Okay. And then I go up the curve again. And then I slide down my tangent. And then I go up the curve again. And then I slide down the tangent. Then I go up the curve again. And then I slide down the tangent. And you can see that if I keep doing this, it kind of just bounces around all over the place. And it doesn't seem to be getting closer to the root. Remember, the root is way over here. Now, in fact, if I bounce and I round it right below the critical point, let's say here, then when I draw the tangent line, this is going to be a horizontal tangent, and it's going to shoot me off to infinity, and then I wouldn't even get close to the root at all. Here's another situation in which Newton's method fails. So this time, we call this an oscillation of period 2. So let's say that I start here. Now remember, the 0 is right here. This is where the root is. So let's say I started with approximation here of x1. And I go up to the curve. And then I slide down the tangent. And then you'll notice I have to go down to the curve, which is here. And then when I draw this, I'm going to slide down to the tangent to my x-axis again. But notice I end up in the same spot. So this is just oscillating, and this will never hit where my root is. So this is Newton's method doesn't work here, or it doesn't work very well. So roughly the number of places of accuracy will double with each step. So let's take a look at how this works. So the formula isn't that difficult. So let's say that our current guess is, I'm going to kind of call this informant. Let's say the current guess is my old value. So I'm going to call it x sub old. So you want to know where the tangent at x sub old hits the x-axis. Okay. So remember, we go out from x old, slide down the tangent, and it's going to hit the x-axis. So the tangent line, remember, has a slope of f prime of x of whatever that value is, that x old value. And it passes through the point x sub old. So x sub old and f of x sub old. So the equation would look something like this. Y minus f of x sub old equals f prime of x of the old value times x minus x of the old value. So we're saying that this is the tangent line equation. I'm using the old value. So this is the slope of the point at that old value, and then that x of old and f of x of old, that would be the point on the curve. So we're going to set y equal to 0 because we want to find the x-intercept. So we now have, let me scroll this up. So we have 0 minus f of x old value equal f prime of x of the old value times x minus x old value. Okay, so I'm going to divide by f prime of the old value. So I get x minus x old value. Because remember, what we're trying to do is we're trying to find the new value. So actually what I'll do is I'm going to write x new. So this will be my, and I forgot to do this. So when we set y equal to 0 to find the x-intercept, that new value, that new x value, I'm going to call that x of new. So that will be my new value. So I'm going to isolate the x of new by adding my x old to the other side. So my new value, my x new value, is equal to the x of old value, take away f of x old, divided by f prime of the x of the old value. So this is the formula for Newton's method. Put a box around this. So note that if you luck out and you hit a root, and the x of old value is equal to 0, and then f of x new is equal to x of old, then the procedure stabilizes and you found the root. Okay. So in general, the formula for the sequence of approximations is, now instead of using all this informal new and old notation, we can say that, let's say the original was x sub n, and then the new value that I want will be one more than that. So I'm going to call it x sub n plus 1. Minus, now notice all of these are old values, so the f of x sub n divided by f prime of x sub n. Okay, now what is n? N is equal to 1, 2, 3, and so on, meaning those are the values of x as we get closer and closer. So I'm actually going to put a box around this one as well. This is actually the formal notation for Newton's method. And I would say the other one is more formal, but helps you understand where the numbers are coming from. So let's use Newton's method to approximate a solution. So let's say that we have this cubic function, and I want to find out where is the x-axis. So my initial approximation that I'm going to use, sometimes it's given to you. On this one, I'm going to give you that the x sub 1 value is negative 0.3. Okay, so I need to find the derivative. Oops, sorry. And we have f prime of x is equal to 3x squared plus 3. So I have my first value, my x1. So to find my x2, okay, according here, I use my old value, negative 0.3. And I'm going to take away, and I'm going to take the negative 0.3, I'm going to plug it into the original function, divided by the same value, negative 0.3, plugged into my derivative. So I have negative 0.3 cubed plus 3 times negative 0.3 plus 1, all divided by 3 times negative 0.3 all squared plus 3. All right, so we plug all of this into the calculator, and you actually get negative 0.322324159. All right, so this is my x sub 2 value. So then to find my x sub 3 value, right, so since this is a third value, that means that n must be now 2. Now I'm going to take my new approximation, because remember my x value should be closer to my real root. I'm going to now take this value. So let's just call this x sub 2 to make it easier for me to show you what and how to plug this in. So now I'm going to say x sub 2 minus f of x sub 2, which means I'm going to take the number, that negative 0.322232459, plug it into the x value here, all divided by f prime, and taking this negative 0.322324159 and plugging it into the derivative. So that would be my denominator. Now when you do this, you get negative 0.32218533603. Excuse me. And you keep continuing this, and you get x sub 4, which is negative 0.32218533546. Now let's do this one more time. Now we're going to use this as my old value, negative 0.32218533546. So we now notice that on my calculator, it's kind of stabilized when I get to the fifth approximation because the values are the same. So we would then say that this S sub 5 would be the solution. Now, one really handy thing that you can do with your graphing calculator is to actually type this Newton's method formula for this question into your graphing calculator, but instead of typing it as negative 0.3, type it in as x, and then you can store that value, and then when you get the new value, you're going to restore that value as your x value, which you can then keep reiterating until you get to the point where the numbers don't change. Now I'm going to show you one more thing here. I'm going to show you how to use Newton's method to calculate a square root algorithm. So we know that the positive solution to x squared minus 3 is going to be root 3. So we're going to apply Newton's method to figure out what the solution is. So I need to figure out the derivative, and that's going to be 2x. So using Newton's method, my new value, my n plus 1, is equal to my old value, x sub n, minus x sub n squared minus 3 divided by 2 times x sub n. Now I'm actually going to do a little bit of simplifying, and I'm going to get a common denominator. So I get 2x sub n squared minus x sub n squared minus 3, all divided by 2x sub n. In my numerator, I can simplify this to be x sub n all squared. Minus 3, sorry, and divided by 2x sub n. And now what I'm going to do is I'm going to factor, so I get half. And when I divide over here, I'm going to have x sub n. And then on this side over here, I'm going to have 3 divided by x sub n. Now, the 3 is because of this x squared minus 3, and that's what I'm trying to find the square root of. So actually, I'm going to convert this, and I could also say this would be half x sub n minus c x sub n. And by using this formula, the c could be used to calculate any value. All right, so I'm going to have an initial guess. I'm going to say that x1 is 1. And when I plug that into here, I can see that I get 1 minus 3, so that's negative 2. Negative 2 times half is going to be 1. Oh, actually, you know what? I just realized I made a little mistake when I distributed. This is a common thing. So when I distributed the negative, I forgot to make that to become positive. So I'm going to bring that down. All right, so let's try that again. So I have 1, plug that in. 1 plus 3 is 4. And then 4 divided by 2 is 2. So my x2 value is 2. And I'm going to keep doing this. And I get 1.75 for x3. x4 is 1.7321428857. And then x sub 5 is 1.732050. Excuse me, 081. And actually, when I calculate this on the calculator, the square root of 3 is actually 1.732050,808. So my approximation is very close.